So according to Drude-Lorentz pre-electron theory, the electrons are free to move within the entire volume of conductor with no potential acts on them. Also, the potential produced by uh, positive ion cores inside the metal is found to be constant. Okay, again, this theory has neglected or ignored the mutual repulsive forces between electrons, and the total energy purchased by electrons is only kinetic. So by considering these assumptions, we have derived the expression for electrical conductivity, thermal conductivity, and the Weidmann-Franz law. So while studying all these physical properties, finally we came across some limitations. Okay, in the previous lecture, we have also discussed about the limitations which are arised in the Drude-Lorentz pre-electron theory. So to remove these limitations, the Sommerfeld had tried to think about the electron contribution for conduction of heat and current with a new approach. So some of the limitations which are mainly arised in the Drude-Lorentz pre-electron theory are listed here. That is, the Drude and Lorentz has certain limitations regarding the explanation of specific heats of metals and insulators. There should be very small, actually in practice there should be very small difference between specific heat of metals and insulators, but as far as the Drude-Lorentz approach is concerned, the specific heat of insulators is found to be 1.5 times that of the metals. So such a huge difference between specific heats is the one of the major drawback of this theory. Again, he has found certain difficulty in calculating the mean free path length, though he has considered that the motion of electrons during or between any two successive collisions is the Brownian motion, and the path length is called mean free path length. But he has not succeeded in calculating that mean free path length. Again, he found that there is a dependence of paramagnetic susceptibility on temperature. Okay, so to minimize these difficulties, the Sommerfeld has think a new approach in 1928 and tries to remove these limitations by using quantum mechanical theory, because I have already told you that the Drude-Lorentz pre-electron theory is totally based on classical approach. According to this, he considered the electrons as a particles or neutral particles that are similar to particles in Maxwell-Boltzmann statistics. Okay, he has simply ignored the charge of electrons, but the Sommerfeld considered the quantum mechanical theory, and the theory also combines with the Fermi-Dirac statistics. He has considered the electrons as the fermions. Okay, you know very well about the Fermi-Dirac statistics, fermions, bosons, and the neutral particles. As far as the quantum mechanical approach is concerned, the electrons are having half spin. So half spin particles are called fermions. They are distributed or classified according to Fermi-Dirac distribution law, and the Fermi-Dirac statistics of distribution is applied to those electrons. Okay, again, according to this theory, he considered that the electric potential produced by positive ions inside the metal is periodic in nature. Okay, I have already told you about the periodic potential while discussing the Drude-Lorentz pre-electron theory. So here, see in the figure, the potential produced by positive ions is a periodic potential. which is actually the case, practical case. Okay, so such kind of potential is periodic potential. Here these solid dots, they are the positive ions which are fixed in at the particular positions in the metal or inside the conductor, and the potential produced by these positive ions are very high near the ions, and as we move away from the ion, the potential goes on decreases. Okay, so such kind of periodically varying potential is considered in and metal. Okay, in a metal, according to the Sommerfeld theory, though the potential produced by positive ions is constant as considered by the Drude-Lorentz free electron theory. So there is certain difference between Sommerfeld theory and the Drude-Lorentz free electron theory. Okay, this theory is based on quantum mechanical approach, and he has considered the spin of electrons, and according to the spin the electrons are treated as a fermions, and therefore they are distributed about or distributed uh, by using the Fermi Dirac statistics. Hello. So again, in the previous theory, we have considered that the all the electrons are responsible for conduction of current and conduction of heat. तुम्हाला ऐकायला येत आहे का व्यवस्थित? हॅलो. येत आहे ना व्यवस्थित ऐकायला? ओके. मध्ये काहीतरी डिस्टर्बन्स आला होता. Again, in the Drude-Lorentz free electron theory, the all the electrons are responsible for conduction of heat and electric current. Okay, but according to the Sommerfeld theory, the electrons in the vicinity of Fermi level can absorb the energy, that is they can participate in conduction of heat and electric current, but not all the electrons can. So electrons in the vicinity of Fermi level means the electrons having energy which is close to the energy of Fermi energy level. Okay, only those electrons which are neighboring to Fermi energy level or which are neighbor to the Fermi level can participate in the conduction of heat and electric current. But according to the previous theory, they considered that all electrons can or all electrons are responsible for conduction of current and conduction of the heat. Okay, so here there is a certain change again, as there is a this theory also put some restrictions on the occupation of energy levels by electrons. So we know these restrictions are put here because of the Fermi Dirac statistics. According to this theory, they consider the electrons as a fermions, and we know there is a limitations on occupation of fermions in a particular energy level, because according to the Fermi Dirac statistics, where the Pauli's exclusion principle is also applicable. Okay, so according to this, only two electrons can be absorbed or can occupy in a single energy level, but not the any number of electrons. Whereas in the previous theory, they treated the electrons as particles of gas, and therefore the single energy level can have number of particles. A number of electrons can have same energy value. But according to Sommerfeld theory, he applied the FD statistics and considered the electrons as a fermions. Therefore, he put some restrictions on the occupation of energy level by electron. Therefore, maximum two electrons having parallel and the anti-parallel spin can be occupied in a single energy level. Okay, so a single electron can have single energy value. No two electrons in a metal or in an atom can have same energy value. Okay, so it is again difference. And on the basis of these assumptions, let us have to discuss the problem of three electron gas in one dimensional box. Okay, so these all these assumptions we have to apply for solving the problem of three electron gas in one dimensional box. So on the basis of this theory, we have to see the application of three electron gas, okay, but in one dimension. Okay, so let us discuss about this problem. Now see the free electron gas in one dimensional box. Here we have the one dimensional box. Let us imagine about the one dimensional box. One dimensional box means a box in a particular line. Okay, along the particular line, that is called one dimension. We know about the two dimensions. X and y direction means the electron can move along the this direction or along the this direction. That means in a particular rectangle electron can free to move, but in a single plane, not in the space. Okay, but whenever we consider the three-dimensional box means electron can freely move in a box. Okay, cubical box or any rectangular blocks. But let us see here, the electron have a one dimensional box means we have to consider the motion of electron in one dimension. That means along the one line. Okay, along the one line. Here we know whenever the electrons are considered as a free particle, the potential acting on electrons should be zero. Okay, so let us see here the three electron gas in one dimensional box of length L along x-axis. As the electron is free to move within the length L, where its potential energy is zero. Okay, again, as there is a motion in one dimension, the allowed motion of electron is in the one dimension. Therefore the if the electron tries to move in along the y direction or along the z direction, then its motion is prevented by the high potential. Okay, simply you can take the example of water in one particular container. So we have one beaker, and the beaker has we have taken this some quantity of water. Then the motion of water is restricted within the volume of that beaker. Okay, can water pass through the walls of the beaker? No, it is not possible, because the walls of beaker prevents the water to come out of that box or that beaker. Okay, so we can say that the near the walls or at the walls the potential exerted on water is very high. Therefore the water cannot percolate or cannot simply come out of the that box. Or you can take the example of suppose if you are in a particular room, but the room has no door. Okay, so you can freely move within the room, but you cannot come out of the cannot leave the room. Okay, because it has no door means the walls of that room will prevent your motion, or you the walls of this room can restrict your motion within that room. Okay, so you can say that at the wall the infinite potential is exerted on you. So this infinite potential will restrict your motion. So similarly here, if the electrons is trying to move along the y direction or along the z direction, then its motion is prevented by high potential barrier. Therefore at this position, that means out of the box, here the white color is the allowed region for electron. Okay, up from 0 to L the motion of electron is allowed. Therefore the potential acting on electron here is 0. Out of the box, that means this along left hand side or right hand side of the box, the potential acting on electron is infinite. Again, if the electron tries to move along y direction, it is suppose y direction, then also its potential is infinity. At this point also, the potential acting on electron is infinite. At this point also, potential acting on electron is infinite. Only the electron is allowed to move along this line from 0 to L only. Okay, out of the box or after the length L, the potential is infinity. Before the length L, potential is infinity. Along the y direction, the potential acting on electron is infinity, and along the z direction also, the potential acting on electron is infinity. Okay, so this entire uh, things are mentioned here with the help of equation. So here V of x equals to 0 means potential acting on electron is 0, but for 0 less than equals to x less than equals to L means within the box the potential is 0, and the potential equals to infinity for x less than 0 means before the or at this position. Okay, at this shaded region potential is infinity. Again, after x less than L, sorry, greater than L, x is the any distance or length of the that box which is allowed for electron. Means if x greater than L, that means at this shaded portion, again the potential acting on electron is infinity. Okay, so I think you all got it. So we have to see the this phenomenon which are happened with electron within that restricted region. Okay, now we know the motion of electrons is time independent. Okay, there is no effect of time on motion of electrons. Let us solve for the motion of electrons. We use the Schrodinger's time independent equation for an electron in one dimensional box. As the electron's motion is along one direction, therefore we have chosen the parameter as x. Okay, here x. So Schrodinger equation for one dimension will be d2 psi by dx square plus twice m upon h cross square e minus v psi of x equals to 0, where E is the total energy possessed by electron and V is the potential of electrons. As we know, we have to solve the motion of electron within the box. So inside the potential box, its potential energy is 0. Let us see here. Inside the box, potential energy is 0. So in equation number 1, we will put V equals to 0. The above equation can be written as d2 psi by dx square plus 2m upon h cross square e psi of x equals to 0. That is our equation number 2. Okay, but for sake of simplicity, we put this 2m upon h cross square e, so this quantity equal to k square, so k equals to under root of 2me upon h cross. Okay, hence the above equation 2 becomes d2 psi by dx square plus k square psi of x equals to 0, equation number 3. We know this is a second order differential equation in psi whose solution, the general solution can be written as psi of x equals to a sin kx plus b cos kx. If we solve this equation, then the general solution is having such kind of form. Okay, the values of a, b are different, value of k may be different, but the solution of such kind of equations is having the form given by equation number 4. And where a and b are the constants whose values can be calculated from boundary conditions. So boundary conditions are mentioned in the previous slide. Here this box shows the boundary conditions, means v of x equals to 0 for 0 less than or equal to x and less than or equals to L, means at the first wall the potential vanishes 0, at the second wall the potential vanishes, and again the particle is existed between the box, therefore out of the box the wave function, that is psi, which shows the complete description of particle, is vanishes. Okay, so let us use these boundary conditions. We have first boundary condition, that is for x equals to 0, the wave function psi of x vanishes. Means here I think you have know very well about the wave function psi. You have learned it in the quantum mechanics, but I will tell you in simple words about psi. Here the psi is called the wave function, which gives the entire motion of particle. Okay, entire the phenomenon which are related with the particle, or the complete description of particle, is expressed in terms of the wave function psi. Okay, if for a particular position the wave function has certain value, then we can say that the particle is present there. Okay, so we know the particle is present within the box. If the particle tries to move out of the box, or it comes at the wall, then its wave function vanishes. That means at the wall the particle is not existed. Okay, after or between the walls particle exists, means at the wall particles may not exist. So we can say that for x equals to 0 means at first wall, at this position the wave function vanishes, means psi of x equals to 0 for x equal to 0. Okay, for x equal to 0, psi of x equal to 0. So let us put these conditions in the equation 4. Let us put here psi of x equal to 0 for x equals to 0. Sorry, equation 4 will be 0 equal to a sine kx, k into 0 is sine 0 plus b cos 0. Okay, we know sine 0 equals to 0, so 0 equal to a into 0 plus b into cos of 0 will be 1, so b into 1. So we can write here 0 equals to b into 1, that is b, so we get b equals to 0. Let us put this b equal to 0 in equation number 4. So equation 4, that is the general solution of equation 3, will be psi of x equal to a sine kx. Okay, that is our equation number 5. Okay, now use the second boundary condition. Again, at x equal to L, that means at this position, again the particle may not exist at the wall, second wall of the box. Therefore the wave function psi of x again vanishes. So the second boundary condition will be for x equal to L, psi of x equal to 0. Let us put this boundary condition in the equation number 5. Here psi of x will be 0 for x equal to L. So a sine k into, in place of x we have substituted here L. Okay, we have substituted here L. So equation will be 0 equals to a sine KL. Here we know that the product of sine KL and the A is 0. And we know when the product of two numbers or two quantities is 0, then it simply indicates that either first quantity is 0 or second quantity is 0. Means if we have a product of 2 and 4 equals to, if we considered it is equals to 0, 2 into 4 equals to 0, then it indicates either 2 is a 0 or 4 is a 0. Okay, or if a into 0 equals to 0, so a into 0 equal to 0 means either a is not 0, therefore 0 is there. So here the product of a sine kl is 0, that indicates either a equals to 0 or sine kl equals to 0. But a is a constant quantity which we have used in the equation number 4, but so a is not having a 0 value, therefore the sine kl should be equals to 0. Okay, which is possible only when we know sine of some angle equals to 0. That indicates we know sine 0 equal to 0, sine pi 0, sine 2 pi 0, sine 3 pi 0, sine 4 pi 0. In this way, sine of n pi will be 0. Okay, means here we have considered that sine kl equals to 0. So which is possible only when this angle kl should be equals to n pi. Okay, sine this kl should be equals to n pi, where n equals to 0, 1, 2, 3, 4, and so on. Means the angle should be equal to 0, or n equals to 1 means kl equal to 1 pi, 2 pi, 3 pi, 4 pi, and so on. Then and then sine of kl is 0. Okay, if we solve for k, send this l on denominator of the RHS, so k will be equal to n pi upon l. Okay, so put this value of k in equation number 5. Okay, so the equation 5, that is the general solution, will be psi of x equals to sine a sine n pi upon l into x. Okay, only we have substituted the k equals to n pi upon l in this equation number 5. Okay, so the general solution of equation 3 will be psi n of x. Here I have put the substitute n as a, because here we have considered this solution for nth order equation. Okay, so psi n of x, or simply we can say psi of x equals to a sine n pi upon l into x. Okay, so it is the general solution. Now let us find the value of constant a in the previous equation. In the previous solution, we have only need to find out the value of this constant a. Okay, so for finding the value of a, let us use the normalization condition. Okay, I think you have very well known about the normalization of wave function. We know the probability of finding the particle within the length x equal to 0 to L is 100%. That means that within the box from x equal to 0 to L, the particle must be present there. Means its probability of finding the particle within the length from x equal to 0 to L is 100%, and the 100% probability is shown by number 1. So from the normalization condition, we can write here that integration from 0 to L means within the box psi star x into psi of x into dx will be equals to 1, that is 100%. Okay, but we know psi star of x into psi of x, that is mod of psi square into dx equals to 1. We know this psi of x, the value of psi of x will be from equation number 7, a sine n pi by l into x. Okay, so here psi of x square means a square sine square n pi by l into x into dx. Okay, here a square I have taken out of the integral sign, so in the integral sign 0 to L sine square n pi by L into x dx, we cannot find out the integral of sine square, so for that I have substituted sine square n pi by L into x as a 1 minus cos 2 n pi x upon L. We know the formula of sine square x equal to 1 minus cos 2x upon 2. Okay, actually the formula will be uh, 2 sine square x plus 1 equals to cos 2x, the formula for the double angle. Okay, so I have substituted here in place of sine square, I have substituted 1 minus cos 2 angle, okay, upon 2. Here this 2 is taken out of the integral sign, so it will be a square by 2 in the integral 0 to L 1 minus cos 2 n pi x upon L into dx equals to 1. Here the integral of 1 will be dx, integral of 1 dx equals to x. Let us see here, in the integral sign there should be x minus integral of cos of 2 theta will be sine 2 theta. Okay, And if we put the limits from 0 to L, upper limit will be L. So sine of L and L got cancelled. So sine 2 pi we will get. So sine 2 pi will be, let us see here, integral. So integral will be sine of double angle. I will substitute right here only 2 theta. Okay. When we put the upper limits, so in place of x, there is the L minus sine of here, in place of x I have substituted L, so L and L got cancelled, so we get twice n pi, but sine of twice n pi will be 0. If we put the lower limit is 0, so 0 minus sine of again 0 equals to 0, so all these quantities will be cancel. Only the quantities remains are L minus 0, so it will be L, that is equation simplifies to the form a square by 2 into L equals to 1. If we solve for a, send this 2 on other side, so 2 by L equals to a square, take the square root, so a equal to under root of 2 by L. So put this value of a in the previous equation 7. So equation 7 is sine psi n of x equals to under root of 2 by L into sine n pi by L into x. Equation number 8, that is the wave equation for electron in a one-dimensional box, which is the solution of second order differential equation that explains the motion of electron in a one-dimensional box. So equation 8 is called the wave function or wave equation for electron in one-dimensional box. So it is about the today's topic. Thank you very much.